Hello everyone, welcome to a different kind of video. This video is actually going to be related to 3D computer graphics, and this is a topic that I'm extremely interested in. And I work as a programmer myself as my day job, and I've been working on creating my own 3D software rasterizer from scratch. And so I've been diving into a bunch of different topics, kind of to learn, and as I build out my 3D rasterizer. And one topic that I have been spending a lot of time on is perspective projection. And this is a step during the 3D graphics pipeline process that I kind of understood for a while, but like not fully. I didn't really get it. And I didn't really know how the math worked out. I've always seen the perspective projection matrix and I've used it, but I didn't really understand how to derive it. So I kind of spent some time this whole week, or the past, I don't know, 4 or 5 days, kind of really diving into it. And so I think I have a good understanding of it. And we're going to kind of derive the entire matrix from scratch here. I'm going to try to walk you guys through that process and try to give you guys a visualization of how this works. So obviously the 3D graphics pipeline is a whole process, and one of those steps during going from model space to world space, then you go to camera space, and from camera space, typically the graphics pipeline goes to the perspective projection to go to clipping space. And from clipping space, there's other stuff, and there's the perspective divide that happens that the GPUs do, and you end up getting all the way to, obviously, the 2D coordinates that come to your screen, are displayed on your screen, right? So that's kind of the whole process. But one of those steps is perspective projection. And why you even have perspective projection is to try to help, when you are projecting these 3D objects, in the world, in your sort of 3D environment onto a 2D plane, you have to, one way to do that is with perspective projection, and it kind of gives you that sense of perspective that things farther away are smaller, whereas things closer to you are larger, and kind of gives you that sense of perspective as you're looking at the 2D screen and you're looking at all these 3D objects as they get projected. So anyways, kind of where we're starting with this is kind of giving you a quick overview of like the view frustum and what this even means, right? So we're starting from partway through the graphics pipeline process. So you can kind of think that we're starting in after we've done the camera space transformation. So we have our model, it's been translated somewhere, rotated, scaled, whatever. Then the camera transformation gets applied. So now we're looking at it from some perspective from the camera's point of view. And then from there, we want to take the camera's point of view, sort of transformation, and then do the perspective projection to kind of get it into this clipping space. So from the camera's point of view, we have a coordinate system here. And let's just say, this origin here is where the camera is situated. And we're just looking, this way. So the way I've defined this is we have the positive y-axis here, kind of x-axis going this way, and then the z-axis going this way. And this is a left-handed coordinate system. I'm using a left-handed coordinate system here. I'm using a left-handed coordinate system for my rasterizer, so I did everything in a left-handed coordinate system. Obviously, if you're doing this in a right-handed coordinate system, there's going to be negative signs that won't be here, that would be there if you're doing it in the other coordinate system. So, you'll have to find a different video or just kind of throw negative signs in if you're trying to do this for a right-handed system. But essentially what we have here is what's called the view frustum. And it's essentially the space that we define that the camera is going to be able to see. It's really the space that we define, that the objects that are in our world that the camera is able to see. And so the way we kind of define this view frustum, the shape here, which is kind of like a cut-off volume, a cut-off cone, or sorry, like a pyramid that's been cut off at the tip, is we have our camera point here at the origin, and then we have this sort of square, well, not necessarily square, but the sort of plane here at the front. And so this plane at the front, where the tip got cut off of the pyramid, that's what we call our near plane, our near clipping plane. And then it kind of grows like this, right, like a pyramid, in all four directions like that. And then eventually there's going to be another plane that we cut off on, and that's called the far clipping plane. And you know, there are boundaries to this, right? There's the left, there's this right wall, there's the left wall, there's the top, there's the bottom. So you have this 3D volume contained between those two planes, and anything inside of that is what we're going to define as like what the camera can see. So you might have some large 3D model, bunch of vertices inside of this thing, and if it's in there, that's what we want to display to the user. Anything within this volume is what we want to display to the user. Anything that's outside of this volume is going to be clipped away, which is why these things are called the clipping planes. They're going to be clipped and not visible to the user on their viewport. So the goal for perspective projection is to essentially take this volume and condense it into, well, to transform this space into what's called clipping space. So we want to kind of transform this volume into this sort of unit cube space. So where the origin is here, and then, you know, we still have the plus y, x, and z axes just like we had here, but basically everything, the whole volume between those two planes gets pushed or gets smushed into a unit cube where we range from +1 to -1 on all three axes, where the origin is at the center of this cube. So you have +1 that way, -1 that way, +1 that way, -1 that way, +1 that way, -1 this way along the z. So essentially the cube is, you know, a width of 2 total along any of the axes. And from this clipping space, you know, there will be more transformations that happen to eventually get to that projected, completely projected 2D screen. But for the perspective, for this kind of derivation, this is just what the perspective projection is doing. We're trying to derive how we go from this volume down to this volume. And then, you know, this is after the perspective divide happens and everything. And so that's kind of what we're going to focus on for this video. And really, you'll see this term NDC, but that's called normalized device coordinates. And essentially, that's what this kind of coordinate system here is we're normalizing all of the values, all of the vertices, whatever their values were here, into this range of -1 to +1 on all the axes. That's what it means when we say normalized device coordinates. So we're normalizing everything down to this unit sort of cube. All right, so let's kind of start through our derivation here. So let's just imagine we have a vertex, right? Some vertex inside of this view frustum, you know, x, e, y, e, z, e. And I'm using the subscript e here to represent eye space or the camera space, right? So that's going to be the vertice of our model after the camera transformation. And that's like something we know, right? And really, this is a homogeneous coordinate. So really, I should have like a 1 here. So we typically are representing our vectors here as homogeneous coordinates, where we have a fourth dimension here where it's just 1, which is typically called w. But we'll kind of see why that's important later and why we need that. But to kind of start off, we're going to imagine that we're looking, I have a diagram here. Imagine that we're looking along the x-axis, down this axis, from the side. So we're seeing this right edge is this line here of the near plane, and this right edge of the far plane is this big line. So we're kind of looking at it from the side, right? And we have the camera pointed down the z-axis. What we're trying to derive here is we have our vertex that's in the frustum, x, e, y, e, z, e, and I've drawn, you know, I've kind of dropped the value down here. So this is the y value of the vertex. And we want to find out if you draw a line from that point to our camera, it's going to intersect our near plane. It's going to poke through this near plane somewhere, right? And what we're trying to derive here, looking at it from this perspective, no pun intended, is what the y value would be of that penetrated point along the plane. So it's going to hit through this plane at some point. What we're trying to derive is the height, right? For right now, we're going to do the x as well, but what we care about is this height. So what is that y value at whatever point it hits at, right? Because this could be any point in space, and if I choose a different point, it would intersect at a different y value. And so to do this, we define a couple of things. So we have this variable n, which is the distance from the camera, the origin, to the near plane. And we have a distance f, which is the distance from the origin to the far plane. And if we have drawn this like I have, what we have here, and also there's an angle which I defined between, kind of the vertical angle between the top and bottom sort of planes there. That is the vertical field of view, which we're defining there, theta. But with everything kind of as I defined here, we can figure out what this triangle, this height of this side of the triangle is. So we have basically two triangles here. We have this triangle, this small one, and this big one, which is inside of the small one is just a scaled down version of that larger triangle, right? So from geometry, the term for this is called similar triangles, where you basically just have two triangles where they have the same angle, theta, and it's a right triangle, and they're just kind of scaled down versions of each other. So that means the ratio of their two sides, that's not the hypotenuse, are going to be equal. The ratios are going to be equal because it's just a scaled up and down version of each other. So what we can say is that this side divided by this side, so yp over n, that's equal to the same sides on the larger one. So this side divided by this side, so ye over ze. And what that allows us to do is calculate yp. So yp is our projected y coordinate onto the near plane. And that's just equal to n times ye over ze, right? Just multiplying by n on both sides. Now, that was pretty simple. It's pretty easy to get that result. And you can do the same for x if you just imagine that instead of looking from the side, now you're looking from the top down. So imagine instead of this being y, this is x, and we're looking from the top. So this is the top of the camera, and this is the width, right? We're looking at this angle, right? And so we're trying to find, and so this coordinate is not y, but it's x, right? It could be over here too. So if you just kind of change how you're thinking about this picture, you can imagine it's the exact same setup, just looking at it from a different perspective. And so deriving this result for y and for x is exactly the same process. You're just using this similar triangle approach, where instead of this being ye and yp, this is xe and xp, and you get the same exact thing. So we have these two equations, yp and xp, that kind of define what the x and y coordinates would be of any point in our view frustum onto this near plane, right? And this is a common result which you might have seen before, but we're going to kind of walk through a bit more in depth on this because we have to do quite a lot to kind of get our final matrix. So anyways, I kind of rewrote our xp and yp here, and there's some extra stuff which I'll get to, but for now just kind of focus on this line right here. And so we have these projected coordinates, right? And those could be anything, right? Because that projected near plane isn't the range of the height and width of that plane isn't -1 to 1. We haven't done anything to it. It's just we just projected the vertex onto that plane. And so the value might be 200, 100. I don't know. It could be anything. So what we need to do is scale that result, our XP, YP vertex. We need to scale that result into the ranges of -1 and +1 along both the X and Y axes. So what I've done here is I've kind of drawn that near plane here, and you know the origin is at the center, like that's the middle is our 0, 0, and I drew a point here, XP, YP. So just imagine that's some point that was in the view frustum, and that's the point where that line is intersecting that near plane. And I've defined two sort of values here, T and R, where T is kind of the height here, and R is the width. Well, the half height and half widths, really. But we're going to use these values to kind of derive some important things. So R is just the width here, right from our 0 over to our right side, and T is the height from this 0, 0 point up to our top point. So it's just how high that is. And we can define something called the aspect ratio, right? If you're familiar with just computer monitors, you know that, or TVs, you know there's something called an aspect ratio. And what the aspect ratio is just a fraction or a ratio between the width and height of the monitor or display or the viewport. So I'm going to define the aspect ratio here as just R, the width, divided by T, right? And just kind of looking at this result, we can actually use R and T to kind of scale our X and Y values down to a range that we want. So let's just say, for example, our XP value was 500, and let's say R was 1,000, right? So if X is 500 and R is 1,000, then our point here is halfway between our center and the edge, the right edge, right? And if you take 500 and divide it by R, you get 0.5, right? So that basically scaled our value down to a range of between 0 and 1 for that side. And if you did on the other side, you would get a negative value. So if you divide X by R, that width, then what you have is the exact sort of range clamping that we need. So this is what we're going to do. And the same for Y, right? If Y was like 200 and T is 800, and you divided Y by T, you get 0.25, right? For here. So it's a fourth of the way up, which makes sense. So really what we're going to do is we're going to take X and Y and essentially divide them by T. And what we're going to do here is, I'm just trying to remind myself, right, so I kind of rewrote these equations here. So what we want to do is we have these projected coordinates, but that's not our final thing we want. What we want is our coordinates projected, but also scaled between -1 and 1, right? So I'm going to relabel XP and YP to XN, YN for the normalized coordinates. So XN is going to be XP divided by R, which is just this. So XP was this, and now we just divide by R. And YN is just YP divided by T. So here I divided that by T. So we have equations now that kind of define these normalized coordinates we're looking for, but there's still some kind of unknowns here. We want to define these equations in terms of things that we're going to be able to know sort of at compile time or whatever in our program, at runtime. So using this sort of picture I drew here, we can kind of get some equations for T and R in terms of the aspect ratio and some of these other values like N and things like the distance of the near plane and stuff, which we can define. So I kind of redrew this picture from the side that we were looking at earlier. So, for example, this is the y-axis, right? So we're looking at it from the side, right? the camera's looking down the z-axis. If this, and that means this line here, this is the near plane, right? Just to kind of remind you that that picture is just this picture. So we're kind of focusing in on just this smaller section here instead of zooming out. So we kind of zoomed in on that little small part, right? So theta, the full angle here, that's our field of view, vertical field of view. And then this distance is n, and this distance is t, right? This is the distance from our origin up, right? We're just looking at this from the side now. So what we can derive here is our relationship. So we can use the tangent, right? Tangent is opposite over adjacent, and we're going to use just the top right triangle. So really the angle here is not theta, it's theta over 2. It's half of theta. And so tangent of this angle, theta over 2, is equal to opposite, which is t, divided by n, the adjacent side. And so t can be derived in terms of n, which that's something we can define, the distance to the near plane. And then tangent of theta over 2, theta is also something we can define. We can define our own field of view that we want. Okay, so we have t. Now, how do we get r? Well, we know t, the aspect ratio, is something that we can also define. That's just going to be our monitor or our viewport. It's width divided by height, right? So that's something we can have. So let's define r in terms of t and the aspect ratio. So if we take the aspect ratio equation and plug in t, this here, what we get for r is just t times the aspect ratio, or n times tangent of theta over 2 times the aspect ratio. So essentially what we have now are these two equations, right? Let's go back, kind of reevaluate what we've done here. We have t, we have r. We have these equations for our x and y coordinates. These are going to be the normalized coordinates. We've done the normalization here. We've derived what these values need to be to kind of normalize x and y down to a range of -1 and 1. And so if we plug in t and r here, for here, what we get is our normalized x coordinate is our I coordinate for x, divided by the aspect ratio times tangent of theta over 2 times the z coordinate, right? And this is kind of like the perspective divide happening here. And then the y coordinate, right, we just take this equation, and you'll notice that the n that was out here is getting canceled because there's an n in r and t. So when that goes to the bottom, the n on top gets canceled. So the n goes away. That's what's happening to the n. So it's going to get canceled, and what we have here is that ye is ze times tangent of theta over 2. Okay. So we've done about half the work here to kind of get to where we're at. Right? We've done x, we've done y, and now we need to kind of figure out z. And I'm going to kind of put this into matrix form here in just a second to kind of help reason out what we need to do to get z. But I've rewritten xn and yn here slightly. So you can see here that I actually multiplied the z here. I multiplied that out onto the other side. So xn times z and yn times z. And then I rewrote all of this in terms of n and r again, and n and t, like I did over here, because I didn't want to write out aspect ratio times tangent of theta over 2. I didn't want to write all that out every time. So I'm going to keep it in this form for now, with n and r and n and t, just to keep it simple. But you can plug that back in at the end. So let's think about what we have to do here, right? Our goal is to come up with a transformation. And when you hear transformation, that should ring a bell. That should be, hey, that's a matrix. I need some matrix that I can multiply by my original I coordinate homogeneous vertex here, right? This is just our vertex that's inside of the view frustum somewhere, right? that's going to be some vertex that's in here. That's some coordinate that we know. And we need a matrix to multiply that. And eventually what we want, if you do the multiplication, is to get this, right? Some normalized x coordinate, normalized y coordinate, normalized z coordinate, and then 1 down here in the w. And because we have a 1 down here in the w, and this would be our coordinates inside of that clipping space. It would be the coordinates that are normalized inside of this clipping space. So we would have x, y, and z would have values between -1 and 1. It would be inside of this cube. And that's our goal with the perspective projection. So how can we do this with a matrix, right? Like, if you just think about this equation here before I did this, if you tried to multiply, if you try to just think about a matrix that could do, you multiply x by something using this row and this row for y, like, you're not going to be able to find a way to get z on the bottom, essentially, the ze value. There's no matrix multiplication that's going to be able to achieve that for you. But why I rewrote it this way, where I multiplied the z out for the denominator, is because this, if you look at this equation, this is essentially just the dot product of what I have here. So xn times ze is equal to n over r times xe. So to achieve this with the matrix, we would just have a row in our top row, because it's top row. I'm in a column major. I'm doing column major sort of matrix multiplication here. But to do this matrix multiplication, it would be this value times x plus this times y plus this times z plus this times w. And that would give us this. So, but n over r times xe, that's not equal to xn. That's equal to xn times ze. So that's why I have this intermediate sort of vector here. So if we did this matrix multiplication, we would have ze times xn for this coordinate. And the reason I have that is, and the same for y, right? So y, n over t times y is equal to yn times ze. So if I put an n over t in this spot on the matrix, when I multiply this out, I get n over t times y equals yn times ze. So I get this equation when I do the matrix multiplication out. And that's effectively, that's giving us these ze's here, but that's not what we want, right? We want to just have xn, yn. So what it looks like we need to do is divide. We're going to have to divide that ze out. So, the smart graphics programmers, when they kind of face this problem where they realize that they're not going to be able to get the ze just from this matrix, there's a step that the graphics cards typically do called the perspective divide. And what we have to do is the result of our matrix here, our projection matrix, we're gonna multiply our projection matrix by our vertex. We're gonna get another homogeneous vertex, but then we're gonna have to take that one and divide it by z, and then after we divided it by z, that's gonna give us the coordinate that we want, the normalized coordinate. So I'm constructing this matrix here so that we get everything we need here, and we just have to divide it by z, and then we'll be good. So that's kind of why I wrote it in this form, because it makes it a bit more clear why we're writing the matrix like this. Now, you might ask, okay, well, z, we still need to figure out like how that's going to transform. We know how x and y transform, but what about this w, right? Well, w starts as a 1, and it needs to end as a 1. Like, w really is just there to kind of help us out for various reasons, like translations and things, but this homogeneous coordinate just needs to stay as 1. Well, if we're going to divide by ze eventually, then this w coordinate needs to be ze, because ze divided by ze is 1. So what we want is, when we multiply our projection matrix by this vector, we get ze here. So this last row I put a 1 here because when I do the matrix multiplication, 0 plus 0 plus ZE plus 0, you just get ZE in that last entry, and that effectively copies ZE into our matrix so that we really don't lose that data. And then when we do the perspective divide, that ZE goes away, that ZE goes away, that ZE will go away, we'll see that later, and then we get a 1 here, which gives us what we need. And this perspective divide isn't something that we typically do like ourselves, it's something that the GPU does, but I'm doing a software rasterizer right now, so I actually have to manually do that, but regardless, that's kind of the motivation here. So we've effectively figured out most of our matrix that we need. We have an n over r here, and remember, r is this, sorry, and t is this. So when you make this matrix in code, you need to like plug r and t here into those spots, right? It's like the aspect ratio times the tangent of theta over 2, like those kind of things. But it's just easy to write it this way. But how is z going to transform? Like, because, you know, on a 2D screen, you might think, well, why do we care about the z, right? We're just projecting it on the 2D screen. Well, no, we're not projecting onto a 2D screen yet. We're projecting into clipping space. And clipping space is that unit cube, right? So there's a depth to this cube, and the depth is, you know, it has a width of 2, but it ranges from positive 1 to minus 1 on either side of the origin. So what we need to do is you know, map the z coordinate of our vertex inside of the view frustum to some z value between minus 1 and 1. All right, so, I mean, the x and y coordinates aren't going to affect that at all. So I put a 0 here and a 0 here because when we do the matrix multiplication of this row times this, you know, 0 plus 0, so the x and y isn't going to affect how z transforms. But then this entry and this entry could, like, the z value definitely is going to affect how the z transforms somehow, and all that we have left is this fourth coordinate. So there's got to be some relationship here to kind of figure out how our z transforms. So I just put in a and b as a variable to kind of figure this out. So if you perform this matrix multiplication, what you end up getting is a times ze plus b times, well, just plus b, right? This would be multiplied by 1. And this is going to be equal to ze times zn, right? Because when we do our perspective projection, we're not getting our normalized coordinates yet. We have to divide it by ze. So this multiplication should give us ze times zn. And then after the perspective divide, then our normalized, our zn, right? We divided both sides by ze. So zn is equal to a plus b over ze. So this equation is kind of giving us what we need here, because we know that we know the range that we want zn to be, minus 1 and 1, and ze, the range of that is going to be the distance, is going to be the near and far planes, right? Our vertex inside of the view frustum, ze, can only range somewhere between this z value and this z value, those clipping planes. So when z is equal to this clipping plane, this front one, it should be minus 1. And when z is at the far plane, right, it's literally on the plane, it should be equal to plus 1, right? So that it's constrained within this unit cube. So we have two constraints with this equation, right? So I wrote two equations out. So when zn is minus 1, ze should be n, the distance to the near plane. And then when zn is 1, then ze should be f, or the distance to the far plane. And so we have two equations here, and we have two unknowns, a and b. So this is effectively just solving a system of equations at this point. And I just did this algebraically. I mean, you could do this using matrices too, but I just did this algebraically to kind of do it myself, really. So here's what I did. I'll kind of walk you through the math here as best as I can. So what I did was I took this first equation, I put it over here, Well, I think I did. Yeah, so what I'm doing here is I am multiplying the n over, right? So we have minus n equal to an, right? Because I had to multiply each term by n. So minus n equals an plus b. Then I'm solving for b here first. So I just move everything over. So b, right, I kind of flipped it around, but b is equal to minus n minus an, right? I had to move it over. And then I just factored out here, I guess. It didn't really matter, but I just factored out the minus n. So b is equal to minus n times 1 plus a. Okay? So I kind of boxed that result because I solved for b in terms of a. Now I want to take this result and plug it in for b in the second equation. So I took the second equation and I plugged b in here. So we have 1 equals a plus, and on top we have minus n times 1 plus a over f. Remember, f and n, these are just the near and far z distances of those two planes. Then I multiplied this by f over f to give it a common denominator so that we can write everything under one fraction. So then we have af minus n, and I kind of just, I distributed the minus n through the parentheses, so I got rid of the parentheses. So we have af minus n minus na all over f. Then just doing some more stuff. I'm trying to solve for a here, right? That's our goal. So then I factored out the a out of these two terms. So if 1 equals a factored out times f minus n over f. Okay, so then I took that result up here. And over here, what I did was we have 1 is equal to a times f minus n over f. And then I took the minus n over f term and kind of put it on its own. So now I just kind of broke up the fraction again, I guess. And then I solved here. So let me just be sure what I'm doing here. Yeah, so f, okay, I multiplied f on both sides. So f, I multiplied every term by f. So we get f equals a times f minus n minus n. So if you just imagine I multiply this term by f, this term by f, this by f, that's what gives me this. And now I can just add n over, so f plus n, and then divide by f minus n, and that's how we get our a. So it's a lot of algebraic manipulation. Maybe I did it like a long way, I don't know, but I eventually got to separating out the a. So this is our a value. So this is what we plug in to our matrix here. This is going into our projection matrix. So our a value, what we're going to multiply by z, is far plus near term divided by far minus near term. Okay? Now that we have a, let's just plug it back into our equation here for b, right? So b equals minus n times, and then I had to plug in I think I started here actually. So b equals minus n times 1 plus a. So then b equals minus n times 1 plus a. So I plugged in our value for a, so f plus n over f minus n. Then I multiplied, I made this 1, I rewrote 1 as f minus n over f minus n. So basically like multiplying just 1, like it's the same thing as writing 1, right? The same thing divided by itself is just 1. But I did it this way to kind of get the common denominator. And then I rewrote it here with the common denominator. So b equals minus n times f minus n plus f plus n all over f minus n. And so we have f plus f on the top here. Should be f. I don't know, it looks kind of like an R. That's an f. F plus f, and then minus n plus n. Those are going to cancel. Minus n plus n is just 0. So what we end up with on the top is just, we get minus n equals 2f over f minus n. And then I just got rid of the parentheses and moved the n on top. So b is equal to minus 2 times f times n all over f minus n. And that's our b term. And that is going into our matrix entry here. That gets multiplied by our w coordinate. And so effectively our z coordinate, when we do that multiplication out, our z mapping ends up being, you know, these two factors of the far and near planes are kind of, one's kind of scaling and then one's kind of doing an offset kind of action. So there's some other videos out there, which I'll try to link, that kind of go into a more geometric visualization of kind of how that works. But I mean, this is a more mathy approach, and this is the way I really like to think and try to derive things. So anyways, this is our projection matrix, right? We have A, we have B, we kind of derived the rest of the terms here. So this is it. This is the projection matrix. You can plug this into code, and I'll show that here in a second. But you just plug this into code. You take your vertexes after they've been transformed by a world matrix, and then a camera matrix, and then once you have that camera view, then you multiply by the projection matrix, and you'll get your normalized coordinates, and you do your perspective divide, and all that kind of stuff. And that's kind of how the graphics pipeline works. But anyways, this was very satisfying for me to kind of derive this, because I saw the equations, I've seen the matrices before. I don't honestly, you can't just look at these terms in the matrix and be like, oh yeah, that makes sense geometrically. It just doesn't make sense to me. The only way this made sense is to just derive the terms myself. So anyways, if you guys have any questions, comments, concerns, clarifications, you have your own insight into this, please feel free to share it in the comments below. I really hope this helps people out. I just kind of did this because I wanted a resource for myself to look back on as well. But yeah, thank you guys for watching. Hope you guys liked it, and I'll see you guys soon.